Hello, welcome to the third video. This one is supposed to be between the second and third lessons of this series on currents, voltages, EMF, series and parallel circuits. To start with a recap of the last two lessons, and then we'll move on to introducing an idea or two which is meant for as a preamble to the next lesson we're going to have coming up soon. Okay, so out of all the things that we talked about in the last two lessons, the first thing I wanted to remind you of was this equation with charge, current and time. If you have it in the form of a triangle, it looks like this, with the charge always on top. And we said that these two, it didn't matter if you switch them over, because 3 times 4 is 12 and 4 times 3 is 12, so it doesn't matter when you multiply two numbers the order in which you do, but when you divide it does matter. So always the Q is on top of the T and you have the I on the other side. The meaning of the current was how many coulombs per second, where coulomb was the unit of charge and seconds is obviously the unit of time. So however much charge flows through a circuit in every second, that's what we call the current. I spoke about this also, that the current in wires is the charge moving, being carried as electrons. So the electrons are part of the metal. The material that you use as a conductor, usually we use copper, but you can use many others. But the property that they have to have is that they have free electrons to move around. Insulators don't really have many of these, so they don't carry currents very well, but metals do. So they have lots of electrons. And what we discussed was that we needed to create a positive and a negative potential on either side of the wire, so that the electrons would be convinced to move along the wire. And when you had that movement happening, we'd call that a current. We also said that due to historical reasons, the electrons go in one direction and they're negative, but we define current as a flow of positive charge. So even though the electrons go in one direction, the actual I, or the current, is always labeled to go in the opposite direction. So that in a circuit like here, the positive side is always the longer part of the battery. You should remember that. The longer part is always the positive here. So that the current is always defined to go out of the positive towards the negative. That's what I is defined to be. But the actual electrons are obviously going to be attracted to the positive, because they themselves are negative, so they would go the opposite way. And I also mentioned, I also said that this is known as a convention. Okay, a convention is something that people agree on, even though it can be sometimes sort of less intuitive than an alternative. It's normally, for historical reasons, it's been used for a while in that way, and then when they discover that the actual charge carriers are negative, it stays as it was before, so that everything is not completely revised, even though the knowledge is new and they understand things slightly differently. Okay, so that was a little bit on current and charge and time. And we also said that the current was the rate of flow. So we had that idea of rate of flow, and I asked you to think about that a little bit, rate of change or rate of flow. And we've seen it before with the rate of change of distance with time, for example. When you have a rate of change of distance, then you say that that's speed, and if it's in a certain direction, that's velocity. Similarly, the rate of change of velocity with time, there's always a rate of change you always do with respect to time, that's called acceleration. So you can say the rate of change of distance with respect to time is velocity, the rate of change of velocity with respect to time is acceleration, and the rate of change of charge with respect to time is called current. More than change, it's flowing through a point, but it's still a rate of flow, or rate of some quantities changing over a certain amount of time, the total amount of charge going through a point, so you can still call it a rate. Now, after talking about all of that, I also introduced you to the ideas of the EMF and the potential difference. And what was interesting about these was, well, there's many interesting things about them, but one of them was that they're both measured with the same units, the volt. Both the EMF, which stands for electromotive force, and the potential difference are both measured in volts. but they have different meanings, even though they both have the same underlying physics behind it and the same underlying units behind it. A volt is the same thing as 1 joule per coulomb, and as you should know, even just from what I was talking about now, coulomb is the unit of charge, right? And the joule is the unit of energy. So actually volt is energy per unit charge. That's the meaning of voltage. That's also the meaning of EMF, and it's also the meaning of the potential difference, since voltage, volts is the unit for those two. Now, what is the difference between them? Well, we discussed this before, but I'll give you a refresher. The idea was that an electric circuit is a little bit like a system with water in it, where you can substitute the idea of water for electric charge, so that if you imagine that this water is the charge carried by the electrons, so the electrons are constituents of the water, they make up the water. If I connect to this water well, I connect a pump, which is here labeled as a P, then I can do something very useful which pumps do, which is that they move water, they get it inside and they give it some energy, and they actually get it to, they can get it to rise, and they can get it to move certainly, but also to rise in height. So this pump is giving potential energy, called gravitational potential energy, to the water by raising its height. Something in physics, something that's higher than something else has more potential energy. It has a capacity to convert its height into movement, and therefore it can do some work along the way, turning some equipment or whatever. So you can, that's how hydroelectric power stations work. They have water which is falling down from a waterfall or a big dam or something, and they use the gravitational energy that they have at the top in order to generate electricity by turning turbines. And in this analogy, this is kind of a metaphor to understand electric circuits a little bit better. What we have is the water falling down. Once it's risen all the way up here, we say that the pump, which is analogous to the EMF, analogous to the battery, gives the water this energy. It gives it the amount of energy which has a certain formula, but that doesn't interest us. Doesn't interest us here. Sorry. So much. We'll look at that later when we do energy. But it gives it a certain amount of energy, and that amount of energy that it gives it, if you divide it by the total charge, that's what we call the EMF. It's the amount of energy given by the battery, or the pump in this case, to the water, or here the amount of energy given by the battery to the electric charge as it goes through it. Now, why is that useful? And why do we distinguish that idea from the potential difference? Well, because the potential difference is all over the circuit. It constitutes these guys. They are drops in energy that the water undergoes as it goes around the circuit. So here there's one drop, right? There's one drop there. Let me draw it just with one drop from there to there. There's also a drop from here to here, right? And the final drop is from here all the way down to the bottom again. There's 3 drops, and they are meant to correspond to this circuit here. What are the 3 drops? Well, the current's going in this direction, conventional current, and the electrons, from the point they're actually going the other way, but if you look at it as the current, then the electrons, as they go from here to here, what they do is that they give some of their energy to this light bulb. That's the symbol for a light bulb, you should know. And that energy is given off then as light, so that the electrons have less energy when they're here than when they're there. Similarly here, the water's got more energy when it's up here than when it's dropped down to here. So in falling from that level to that level, the water gives some energy to the light bulb. And in this analogy, the light bulb is represented by this little windmill there, or this little turbine. And as the turbine is not a windmill, it's a water mill, and as the water falls, it will make the turbine turn. And so you can use that turning effect to in a generator to generate well, useful energy for you. Basically, this drop in energy from there to there is the same idea as the energy being dropped by the electrons from going from here to here, except here there's no change in height. There's change in energy of the electrical potential. Instead of gravitational potential, there is a change in the electrical potential from here to here. Again, you get another drop. After it's gone through there, it drops again through here, and now it can do the same work on another generator, and then again here on the third one. And these correspond to the 3 light bulbs. And hopefully you can see that the total sum is a very important idea. The total sum of this guy plus this drop, those 3 drops, the total sum of them is exactly the same as the total EMF given to the water by the battery in the first place. So that if you have a battery of 6 volts, then the total of those 6 volts is going to be shared between these 3 light bulbs. And if they're all equivalent, exactly with the equal resistances and all of that, we'll talk about resistance later, but if they're all equivalent light bulbs, then there will be 2 volts between this point and that point. There will be 2 volts between that point and this one, and there will be another 2 volts between this one and that one. Total adding 6. Notice that I never say at this point there will be a voltage off. That doesn't make any sense. What we always speak about when we talk of voltage, or sorry, a potential difference, it's more specific, we always talk about the difference between 2 points. Why is that? Because we're talking about a change in energy between one point and another one. You can't, it would be the equivalent of asking what's the energy, what's the height difference between this point and this point. There's no height difference, so it doesn't make sense to speak about the voltage of 1 point. It's always voltage across 2 points as a comparison, as a contrast. That's the potential difference between 2 points. Okay, so you can speak about the change in height between here and here, and that makes sense, that's fine. And similarly you can talk about the change in potential or the potential difference between here and here. Okay, if you put a voltmeter across it, that's why you always connect them in parallel. You can measure the change in energy between here and there. So we talked about all of that, and hopefully that's a refresher for what's going on with those things. And I wanted also to give you a few questions to give you food for thought before the next lesson. So the first question is here. It says, what can you tell me about the change in height of the water that flows through root 1 compared to root 2 in this diagram here that you can see on the right? Okay, so this is a slightly different diagram. It's very similar to the last one, but now look what happens here. There's 2 pipes coming off, and the two sets of water, or whatever you want to call it, the water comes along here, and it comes down here and down here. And the water does the same thing as it was doing before. It goes through a certain number of drops and then returns to the bottom energy right here, and then the pump cycles it around again. So first question is asking you to notice what is going on with the change in height between those two. Okay, it's very important that you notice that, and that you note it down somewhere. You bring it with you to the lesson when we get together again. Okay, so what can you notice about the change in height between the water that goes along route number 2 and route number 1, those 2 routes? Question 2. What happens to the water at point X? This is point X. What happens to the water there? It's a pretty simple question. And question 3 is, if you compare the amount of water falling per second through point Y, I'll highlight point Y, it's here, and point Z, if you compare them, so if you look at the water going per second here, and the water going per second going through this point per second here, you compare these 2 points, what would you expect to measure if you compare those 2 different flows of water through those 2 points? Okay, those are 3 questions that I want you to consider about that. Now all of that is based loosely on what we've been talking about so far, and I wanted to talk a little bit about this, which I believe I also mentioned, but I haven't gone into a lot of detail, and this will be part of our next lesson. Here's an equation which relates the volts, or the voltage, or the potential difference in a circuit between 2 points, potential difference V measured in volts. We normally say voltage equals, but it can be either EMF or potential difference, either one of them. Now I'm just wondering if I made this clear enough. Just before I continue with that, let me just mention here, because I might have jumped it, that I explained what the EMF was. The EMF was the energy that the pump gives to the water, right? In rising it up all that much. But the potential difference, I think I didn't emphasize enough. A potential difference is the potential difference between here and there, okay? And also between here and there, and between here and there. The potential difference is all the drops that the water undergoes as it goes through the circuit. So the water, the electric charge here, as it goes through the circuit, it gives energy to the light bulb. And that energy that it gives, these slots of 2 volts, they're called the potential differences. They are the amount of energy the water gives to the circuit and the components in the circuit, and the EMF is the energy that the water receives from the battery to then go around the circuit. So here there's EMF happening, and the rest of the circuit there's potential difference, or potential differences being undergone, or whatever word you want to use there. Okay, so we'll go back to here. So this is V for voltage, but that could refer as much for EMF as for also potential difference. So let's have a look at what I wanted to talk about here. There's this idea, this is I, as in current. I is always symbolized by an I in electric circuit theory, and the R is standing for something called resistance, which I think I've mentioned a little bit about before. And the resistance is a property of the wire. You have different wires which have different resistances. Resistance means how hard it is for the current to flow through a particular wire, how hard it is for the charge to flow through, and how hard it is to get a large current flowing in that wire. If I have a wire with a very high resistance, it will be very hard for me to get a large current flowing through it. I'm going to need a very large EMF, which can be symbolized by the V. EMF means a pump. If I have a place with a lot, if I have a wire with a lot of resistance, I'm going to need a very big pump to give a lot of energy to the water so that then it can flow through the circuit, even though there's a really large resistance. Now, that means the same EMF, the same pump, where if I was going to use the same pump here for 2 different circuits, and one of them had a lower resistance than the other, it would mean more water flows through the one with the low resistance than flows through the one with the high resistance. I hope that makes sense to you intuitively. And I wanted to talk you to think about this, these different situations here of what's happening with the flow of current and the analogy with the water and the pipes that I've been talking about. It says in the circuits drawn on the left, these 2 circuits in this case, which one do you think will be easier for the current to flow through? And notice this one has 2 bulbs and this one has only 1 light bulb. We're going to assume for this question that the bulbs have exactly the same resistance, the same properties, and this circuit here we call, and we'll talk about this more, I've already mentioned these guys, but it's good to refresh. These are called parallel. This is called a parallel arrangement, where there is current going in one direction, and then this happens with the wires. There's a split in the wires, and then they come together again here. That's called parallel. But in series there's only one route for the guys to take, and this is it. That's called a series circuit. You can connect 20 light bulbs here in series, or you can connect them here in parallel, and you need a branch for each new light bulb. Now the question is, do you think for the same type of battery, okay, same pump, the same battery, and the same type of light bulbs, even though here there's 2 and here there's 1, do you think the water, the charge is going to find it easier to flow through this guy or through that guy? Okay, the same, everything else the same except the 2 bulbs. Where is there going to be a lower opposition for the current to flow? And I would like you to think about that using this analogy that I'm going to give you above. Here's the pipe. It was 1 pipe and water flowing through it. Imagine if the same water came through and it suddenly met with this situation. what's gonna happen? Imagine I'm looking at it from the top, okay? So this is not gravity being pulled down or anything. We're looking at it from the top, so this is kind of right and that's left. What's gonna happen there? And so what do you think that tells you about the question that I just asked you, and what do you think is going to happen with the charge? It's going to flow easier in this one, it's going to flow easier in that one. We'll talk a lot more about this in the class, and I want to see your answers for the questions that I've given you here in when we start the class. The next one coming up. Alright, so I'll see you then. Until then, I hope you're enjoying the physics. Bye bye.